what's inside of that box. We don't publish the data that was used to make that calibration, okay? So that's an important distinction, and I'll talk about this later if I have some time, but that actually gives people the ability to make their own modifications of this model. And so I might have time to show you some of those ideas. So where does these cost estimating relationships come from? So let's rewind back to 1981. In 1981, this formula was published. And this was extremely gender biased. Man month, that's been corrected to person month now, equals 2.4 times thousands of delivered source instructions, KDSI, to the power of 1.05. Todd, we were talking about this nonlinearity earlier, right? So if this exponent was 1, it would be a linear relationship. But because it's slightly above 1, as the number of lines of code increases, you get a nonlinear increase in effort, right? And then there's a variety of cost drivers. So these cost drivers back in 1981 were things like, well, what kind of programming language are you using? And what kind of memory constraints do you have? Again, this is 1981, right? So a very similar cost estimated relationship still exists, although it's been modernized, and we don't call it KDSI anymore, we call it SLOC, software lines of code, right? So that is the primary input in software, okay? And no longer are we dealing with a simple environment where we just have a constant up here. Now there's a bunch of variables that could influence those nonlinearities. And of course, C is not a single, by the way, that's not the speed of light or anything like that. It's something different. Those cost drivers for software, now there are 25 different knobs that you can turn that will influence the cost of the software, right? So building off of that, here's my cost estimating relationship. So let me walk through it from left to right so you can appreciate what are the things we're capturing in a system engineering context. So on the far left, person months, and the subscript for NS is nominal schedule, meaning that there is no dramatic schedule compression going on in the project. We know that projects get compressed all the time, right? We also know that foolishly, some projects are given much more time than necessary, okay? That's another inefficiency that is hard to deal with in cost modeling. They call that Parkinson's law. You experience Parkinson's law almost every day. Parkinson's law says the work expands to the time allowed, right? So if you give a student a deadline on Friday, like it's going to take them until Friday to do it, right? It's just human behavior, right? So we can't really account for that in cost modeling because a lot of times just people work less efficiently when they're given more time. We also can't account for schedule compression all the time because that's an external business pressure that is really, really hard to account for when we collect data. But nevertheless, the initial assumption is no schedule compression for this project, okay? Immediately to the right of the equal sign, we have a calibration constant. So the value for A is influenced by historical data that we go out and collect from those industry participants. So formally it's called calibration constant. I like to call it the fudge factor, right? Because it helps us translate all the technical inputs on the right side of the equation into person month units.
How do you know if your fudge factor is correct, or at least fudging in the right direction?
Yes, right. So what we do is we feed data into the model to calibrate the equation, and then data that we did not use for the calibration we use to test the model to see whether, yeah. And I have a pretty graph to show you how that looks visually later, but essentially we data split. Train the model with half the data, validate the model with the other half. This big parentheses is a weighted sum, and what we're trying to manage is various size inputs. So remember earlier I presented requirements, interfaces, operational scenarios, all of these characteristics of systems that either all or just one can be used to quantify how big the job is. So functional size, not physical size. And the reason why we have a weighted sum is because we know that requirements, for instance, some of them are easy. We apply a weight to easy. Some of them are nominal. We apply a weight to nominal. And some requirements are difficult. So we have a weight to account for that. So a way to distinguish that is a difficult requirement may be something that you've never done before, Or you know it's just inherently expensive because you need a, I don't know, $3 million test facility to even demonstrate that it works, right? Whereas an easy requirement may be something that you've done a million times before, or you're going to buy it off the shelf. So it's not going to cost you too much in engineering effort. It will cost you in licensing fees, but that's a different part of the cost model. So the weighted sum, again, is a way to characterize the functional size of the product. Then we have an exponent there, E. In this case, I am sticking to a constant because I don't have enough data to validate. You would need a lot more degrees of freedom in order to be able to test whether you can have variables up there for the nonlinearity. But I know that there is nonlinearity, and I'm going to show you the data in a little bit. At the end, you have a product of 14 effort multipliers. So capital Pi, again, is just a product. And what those 14 effort multipliers help you characterize is how difficult is this project relative to other things. So this is a relative measure of complexity. Have you done something like this before? Are your people trained in the right tools, right? Are they located in the same time zone or not? All of these questions, the answer to all these questions drive the cost up or down, depending on how you answer them. So let me give you a little bit more detail on some of those 14 effort multipliers. So these are the kinds of things that drive the cost up or down. How well do you understand the requirements? Remember, the takeaway is that is the most significant cost driver in this entire model, requirements understanding. The one that's underlined, stakeholder team cohesion. You're wondering, what is that? Well, that literally means, do people get along? And you would think, what place does that have in an engineering model? Well, I'm sure failed projects you've maybe been a part of or seen, a lot of times it's the interpersonal dynamics that ruin them. So the difficult thing has been to describe something that's very subjective, quantify it, collect some data about it, and validate that it truly does belong on this list, right? Technology risk, I mentioned this one a couple times already. So if the NASA technology readiness scale, 1 through 9, we're at level 1, it's just an idea, not even a prototype, and eventually it graduates to something that's ready for launch at level 9, right? So what Cosismo wants to know is what level of the technology readiness is your project at? Are you at level 3, trying to get to 9? Or are you starting at level 8 and only need to go one level up in order to prove that this is ready for launch? So you can imagine which one is more expensive than the other. I'll just mention one more, migration complexity. This one comes up to bite people very frequently because it basically asks the question, how much of the legacy system do you have to connect to? And if you have to make a interface, special interface, or you have to do a switch over from the old system to the new system and maintain the level of service, that's going to be much more expensive than starting something from scratch, greenfield, right? So that particular driver, often people ignore it, but it drives cost significantly, okay? Because it influences your design, it influences what you can do. The top right covers issues that have to do with people, and I actually borrowed that idea from the software models. As you can imagine, more experienced software programmers make less mistakes, less defects. Same idea in systems engineering. We also quantify things in terms of defects. But even though they are more experienced and create less defects, they're also more expensive, right? So the question often is, well, what's the trade-off? If I'm paying somebody $150 an hour because they are the top programmer, is it worth it? Are they making truly less defects than somebody that I can pay $50 an hour, right? And the answer to that is it depends. So let me actually talk about the technology risk cost driver, just to give you a better sense of how this is quantified. So here's the NASA TRL scale. So again, if you're at level 9, it means that you are ready for launch. There's no additional testing or R&D needed, right? So this translates to a very low, on this end of the scale, very low risk in your project. So if you characterize your project as having this level of technology risk, cost goes down. Okay? Other end of the scale, if you are still tinkering in the laboratory and you need to eventually graduate this technology to something close to level 8 or 9, then you have a very high technology risk. It doesn't mean you won't be successful, it just means you need to invest system engineering person months into that, right? So that's the kind of way that we characterize one of the cost drivers. We typically define the nominal case as being typical. This is sort of the default setting on the model, and you have to make a decision on whether you belong on the right side of nominal or on the left side of nominal. Okay, yeah?
Is it at a technology readiness level, or is it sort of a system readiness level? I mean,
Yeah.
is it driven by something that's lower than systems engineering, you think, or is it driven? You said something interesting, right? Which is if your TRL is low, you might have to invest more systems engineering effort.
Correct.
Okay.
Yeah, so the system readiness level scale came out 5 or 6 years ago, and he doesn't have enough data to validate whether it's significant. Yeah, so I'm sticking to where I can get data. Sort of that's the other constraint that I have is, I mean, I can create, phenomena, parameters just on a back of a napkin, right? But can I get data to validate that it belongs on this list?
You're asking the project manager what was the TRL of some core technology that was in
That's right.
project.
That's right. And actually, the question is more specifically, what was the TRL at the beginning of the project? Because I don't want to know what it was at the end. I want to know what it was at the beginning, because that's where you have to invest the person months. All right. Let me keep going here. So let me just summarize the cost drivers. Numerically, we didn't make these numbers up. These are derived from the calibration, from the historical data, right? So by definition, all the parameters are set to a default of nominal, right? Notice though that if you go to the right of nominal, in some cases it goes below 1, and to the left it goes above 1. In other cases, the polarity is opposite, right? So that is because there's sort of two things that are important there. Whenever you fill out a survey and you just check 5, 5, 5, 5, 5, 5, right? So we avoid that by flipping the question. The other thing is that how you define the phenomena, so requirements understanding and architecture understanding are inherently positive things. So the more of this that you have, the better it is, so you save money, right? Other things like technology risk are negatively phrased parameters. So the more of this that you have, the more, meaning that way, the worse it is for your pocketbook, right? So it's also just how you're describing the phenomena, right? You notice that not all of them are perfectly aligned in terms of a 5-point rating scale. In some cases, there are some gaps here, and sometimes I violate the rule and I go an extra level to extra high, right? So part of this is trying to force fit vocabulary and standards that people understand in industry and trying to collect data for it. So if there were some social scientists here that do parametrics, they'd murder me. I'm violating all sorts of rules, right? But I know that I'm safe doing this because I've validated the model and it works. This is the best arrangement of those numbers, right? So we've experimented with a variety of combinations. Now the column on the far right, EMR is effort multiplier ratio. And the EMR is the ratio of the highest number in that row over the lowest number in that row. So what EMR tells me is what is the dynamic range of that parameter. So what is the best case scenario and what is the worst case scenario. And that allows me to compare them all sort of on the same criterion. And so this Pareto diagram is the EMRs of all of those cost drivers that you saw on the previous slide, but now they're organized by impact. So this was the takeaway. Requirements understanding has the highest EMR value, meaning that this has the biggest swing potential. best case and worst case, it has the biggest. You can think of it as a musical instrument. A piano has 4 octaves. Any musicians in the room? 5 octaves, something, right? A lot, right? Versus a flute. Anybody have like young kids? They play that recorder, right? 1 octave, and out of tune, right? So, one instrument that has a small dynamic range, documentation. Documentation is not going to kill your project. Maybe it will increase cost. Maybe it will provide some productivity, but it's not going to kill your project if you skip documentation. But if you skip this stuff, your project is dead. Level of service requirements. Those are the ilities. Again, survivability, interoperability, manufacturability. The more of those that you have, the more expensive your project is. So from a risk management standpoint, you can think of this as we got to take care of these big ticket items first. And let's not worry about the stuff on the top because it's not going to make or break your project. Let me show you one more item, and I want to leave enough time for questions because I'm curious about what you all think. The way we try to validate some of these projects is by plotting on the x-axis the size of the project in terms of equivalent requirements versus the effort in terms of system engineering hours. Okay, so the idea is that there's a correlation between these things. The bigger the project, the more effort it would take, right? And you generally see that phenomenon here, although it's nonlinear, right? It's like looking kind of flat and then it spikes up there. And then we have this troublemaker over there, right? So in statistics, you would say, well, that's an outlier. Let's throw it out, right? We can't do that in cost modeling because that's a real data point. And what that data point means, and the reason it's so far from the others, may be a problem with the model, right? It's kind of like in baseball. You've heard of Babe Ruth, I'm sure. So in baseball, we have an expression that if you do an analysis of sabermetrics and Babe Ruth doesn't come out as the best player of all time, then there must be something wrong with your analysis, right? Same idea in cost modeling. If there is a project that's sitting out there by itself, then there's something in your model that didn't capture the phenomena, that the uniqueness of that project. So what we do is we calibrate the model, again, using half the data to to train it, and then half the data to validate it. And that's not a hard rule. We sometimes go 75%, 25%, depending on how much data we have. And then once we fine-tune the model, we throw in a similar data set, and the calibrated model looks a little bit more reliable. I'll use that word. It's not a great predictor, right? But at least we see some uniformity. We see some nonlinearity, though. Todd, I'm coming back to that, right? You see that there's some nonlinearity in that. And so in statistics, this is heteroscedasticity, meaning that the larger the data gets, the more spread that you have from the mean. We can live with that, though, because that means that we have optimized the data that we have, and we've minimized the error. But let me tell you what's acceptable in terms of error and cost modeling. If you're off by plus or minus 20%, you're really good. This is the acceptable metric in cost estimating. Now, notice what I said, plus or minus 20%. That's a swing of 40%. But if you are within that error band, you're doing really well, right? So the benefit, so the burden of proof that I had to come up with to demonstrate that this model was good and it was acceptable was, well, how good is it than anything else that's used? Okay, and fortunately, before I built this model, there was no system engineering specific cost model. So the methodology was SWAG, you've heard that term maybe, sophisticated wild ass guess. So that was my competitor. So as long as I was within 20-30%, life was good, right? Now, the challenge is on the table. Anybody that can build a system engineering cost model that is more accurate than this one, then they get a PhD, right? So I want to stop there because I want to leave some time for questions. I've got plenty of more slides, but maybe you want to fire away with Q&A. So, yeah. Oh, okay. Any question? Yeah?
So how do you deal with, for example, so how do you quantify uncertainty, say, in your result here? You've got some regression, and then you've got doing around that.
That's right. So there's actually two. Go ahead and finish. Maybe there was in the second part.
Well, and then I guess to me, what I'm interested in is what's driving that uncertainty. Is there a way? Have you tried to do things like allocating some fraction of that uncertainty to one of those metrics? Like if you had better data on requirements number or something like that, right? I mean, maybe all the information you're getting on requirements is also plus minus 10 requirements or something, right? Because you don't keep all that great a track of it or something. Then how does that influence what the output is?
Yeah. So there are two ways to capture the uncertainty. One of them is essentially because the data is noisy, then the model is uncertain, right? So there's already that embedded into it. And then the other point you brought up is the inputs, once the model is complete, the inputs that are coming into the model are also unreliable. So they're adding more noise. Now, do they cancel each other out? Do they compound? I don't know, right? But I'm just going to have to accept that there's an error at the end. Plus or minus 20% is what I can accept. Now, one way that we quantify how noisy or how uncertain the model is we use these PRED criterions. PRED 30 essentially means plus or minus 30%. PRED 25, plus or minus 25, and then I mentioned earlier the plus or minus 20 criterion. So I won't go into the details, but essentially the model that I'm showing here has a PRED 30 of 100%, meaning that 100% of the time it gets within plus or minus 30%, right? But notice how quickly it drops. And if I was to add an even more stringent criterion, it would drop even farther, right? So I already know that there's noise. Now, I can't eliminate it because the data that I'm collecting is being reported by humans. It's not being collected by a machine. There's no validation of that data, so it's inherently unreliable, right? So as long as you're willing to accept that the data are noisy and that the model is not perfect, then that's the environment that I'm in, right?
I'd be interested, like if you've seen stuff like on system sensitivity analysis and things like that, where you can kind of propagate those input uncertainties to outputs. I'd be interested in what.
Yeah, I mean, I know which.
I guess it's very. I guess your model is quite linear, right? I mean, there's sort of that big linear sum.
Right. Yeah, it's.
I understand those sensitivities pretty well.
I do. I know which of those parameters are the troublemaker, and there's not just how I collect the data, but how I define the parameter is what drives how much noise I get. So I'm just hoping for that signal and reducing the noise as much as possible, but I'm never going to eliminate the noise. Yeah.
In the formula that you showed, there was the calibration constant.
Yeah.
So in that case, you're talking about obtaining historical data. If
Yeah.
there's a new product and we don't have any historical data, what are the changes you do to be able to still be in the plus minus 25%?
Yeah. So this was a problem with NASA, for instance. They built the rover. What was it? The Opportunity and Curiosity. Yeah. Okay. So the price tag on each one of those little robots was $800 million. Okay. So how did they get to that number? Okay. So that was a unique product in terms of what it was able to do, to go to Mars. But that was not the first robot NASA had ever built. So NASA went to their database of robots. They ignored all the satellites and science experiments because those are not relevant to this discussion. So they just looked at robots. They said, okay, let's use that as a baseline. But the Mars rovers are more expensive because they're more complex. The mission is different, right? So at least when you don't have any data, there's actually some estimation by analogy that you can do that either you've done or somebody else has done. Maybe your competitor has done it, right? So you can kind of to a limited extent you can use historical data, But it's not going to answer the entire question about $800 million, that's how much it costs to do the Mars rover. At least it will tell you it will cost at least this much, because the previous robot we did was used on the moon, and that's an easier mission than sending something and saying goodbye to it for a few months and not hearing from it again, right? So,
It's a mixture of causation and swag.
well, and estimation by analogy, yes, yeah. But swag is the most popular estimating methodology we use.
I wonder if there's some relative value to, if it's more valuable to, you sort of, again, maybe presented the data sets as having equal confidence in both directions.
Oh,
I
right.
guess, right? And I wonder if there's value in trying to think about it from the point of view of that it's better to overestimate, or maybe, it's less, I can't think about it enough, but the point is, yeah, maybe it's better to overestimate cost than underestimate cost. Is there higher value on one side
Yeah.
of the line than another side?
Yeah, it's actually a problem that comes up very often, and it basically comes down to the legal aspect of the project. In other words, what kind of contract are you being issued? So the most common type of contract, like almost every research contract, is firm fixed price. Okay, so that has certain legal implications, meaning that if you go over, that's your problem. If you go under, good for you. But I'm not giving you any more money than this firm fixed price, right? So who bears the risk on a firm fixed price contract? You do, the PI, right? Or the contractor, right? The client bears no risk. And there's a spectrum of contract vehicles. The under the spectrum of firm fixed price is cost reimbursable. Who carries the burden on that? The person paying the bill. Because all you do is you're billing them for your time, right? So there's a bunch of flavors in between those. So that determines whether you should pad your estimate or not.
Yeah, so have you thought about, incorporating, I guess it's contract type or something like that?
Yeah.
Is that all, is that also a factor in cost overrun?
Yeah, absolutely. Yeah.
Presumably, yeah.
Yes, we have thought about it. We wrote a paper about it, and it's not a simple solution. Yeah, yeah. And it depends on the industry too. Google doesn't really care about cost overruns. They're printing money, right? But Raytheon does, because they're a publicly traded company, and they're reporting on very thin margins every quarter from the defense industry, right? So, yeah.
I'm going to ask the department head.
Okay, go for it.
I'm not a systems engineer. So that's a really great snapshot or picture, I think, of what your work is. That talk was.
Yep.
So if you moved here to CSU, how is that going to influence your research program? Are you going to take it in any different directions because of collaborations here, or help me understand why moving to CSU would be a good thing for you and your research?
Sure. I think the flavor of the system engineering program here is very heavily industry, and that is the laboratory that I work in. So the more data that I can get from industry, the better, right? More data points, and outside of the aerospace and defense industry as well. So if there's an opportunity to build a version of Cosismo for renewable energy technologies, I don't know, right? Things that don't exist in well, we have solar power over there, but there are things that exist in Colorado, industries that exist here that don't exist in Arizona. So that, from a personal standpoint, that would be a huge benefit. But also having students who are embedded in those companies. That's how you get in. Maybe those become student projects.
Right.
Hey, your project is to build or calibrate this model that already exists, calibrate it to your context. And what that does for me is it gives me more knowledge about how that model needs to change in order to be more versatile, right? Because the end goal, like the software cost models, they've been around for 40 years. So they have a lot more, not just hard data, but they have a lot more institutional experience. So that's how these models improve over time.
Do you work with people in business schools a lot when you do your research?
Yeah, there's some folks in the MIS department that really like the software modeling things, because what they need to teach MBAs, for instance, is not just how to manage the project, but how to make realistic budgets. So I do a lot of guest lectures in the the MBA classes that are dealing with IT systems. Yeah.
When you talk about the documentation driver for the EMR,
Uh-huh.
when you're talking about system of systems,
Yep.
and the amount of interoperability is high, documentation plays a major role in
Sure.
that because each system is tested based on the first system.
Yeah. By the way, you used interoperability, so I'm already going to account for it. Level of service requirements. Thank you. Yeah.
Okay.
So if your question is about documentation, I don't want to double count the penalty. I either account for it in the level of service requirement parameter or documentation, but not both.
But is it still better to estimate it in high, even if I'm just building one system, but as a company, I will build systems similar to that in the future. So
Mhm.
documentation comes somewhere in the middle for future systems.
Yeah, but remember, documentation is not a very expensive thing,
Right.
right? So if you do documentation well, or if you do it poorly, it's in the noise. It's the other parameters that really come back to haunt you. So now it's still up here, so it still made the cut. I mean, there were 50 reasons why system engineering can cost what it does. So I couldn't build a model with an infinite number of parameters. So you have to sort of be realistic and say, well, what's a good manageable number, and then what's the trade-off? Because there's also a statistical trade-off in how many parameters you have and what the accuracy of your model is. So documentation barely made the cut. But the data showed, hey, this is important. It's not the most important, but it's important. Sure. Yeah?
Yeah, this is a model of systems engineering effort or cost. Are there other places where this same approach has been used?
Yeah, so
Or do you see potentials?
yeah, I mean, the sort of two that come to mind is the automotive industry actually has been using for automotive electronics. So they actually asked me to create a version of Cosismo for just automotive electronics. So the inputs were not just plain old interfaces, they were electrical interfaces, so that we were counting. So that's one area, and then the other area that's sort of growing like crazy is app development for smartphones. And this is a software platform, but it's a very different one because it doesn't reside in a traditional environment for software. It resides on a mobile unit or a tablet, right? It's still quantified in terms of lines of code, but there are other reasons why apps cost what they do. So I had to answer that question myself on the football project.
The model changes.
Absolutely.
Okay,
Yep.
now, as far as the objective of the model here is systems engineering cost.
Correct.
Are there other objectives
Yes.
that this, other than system engineering?
Oh, no. This model is only answering